Great. So should I start?
Yes, go ahead.
Okay, great. So thanks for the introduction and thanks for inviting me. So today I'm going to talk about a work which is a bit different from what I do usually. Is not homomorphic encryption. There's going to be a little bit of homomorphic encryption, but this is not the center of the talk. So I'm going to present SANNS, which is a secure protocol for the k-nearest neighbor search. And this is a joint work with Ao Chen from Microsoft Research, Hie Dong from Microsoft, Oksana Puburinaya from the Simons Institute, Ilaria from Microsoft Research, and Sadek Riazi from UC San Diego. So the idea of the paper is to solve this k-nearest neighbor search problem in a secure way, and in particular to try to scale up to large databases. So first of all, what is the nearest neighbors search problem? So the idea is that we have a data set containing endpoints, and those points are real points of dimension d. And we also have a query, which is a point in the same space. And the goal of the k-nearest neighbor search is to find the k points in data set X, which are the closest to the query Q. And the close distance is measured with Euclidean distance. So this is largely studied in the literature and largely used in practical applications, but very often is used in a plain text manner. So the data is not hidden. And what we would like to do, of course, is sometimes to not disclose the data because it's not always acceptable. Let's imagine as instance application where the data that we treat is sensitive, that can be biometric data, medical, financial, and so on. Or there are situations where the law regulation try to protect this data. And this is the case as instance with the GDPR regulations in Europe. So we would like, of course, and many studies in the literature already have started in this direction, to solve this k-nearest neighbor problem in a secure way. So protecting the query, the data set, and the results. So many applications are possible. The majority of them concern similarity search queries in general, where you have a certain amount of feature and you're trying to look for some similarities between your query and those features registered in the data set. So you may think about face recognition applications or biometric identification, any kind of biometric identification, or more in general, database search, like such as the data set containing images or words, and many other applications. So as I said, there is a large amount of works in the literature that already have solved this problem. And in the case of a two-party computation setting, the majority of the solutions that we find in the literature are based on linear scan. So the linear scan is it's a very easy concept. You just take your query and you compute the distance between the query and all the points in the dataset. And once you have computed those distances, you will select the top k elements. So the elements that have the smallest distance in this list. So in general, the distance computation is done in different ways. We have solutions that use the Payet crypto system proposed by Pascal Payet in 1999, which is an additive homomorphic encryption scheme. Some other solutions use a fully homomorphic encryption scheme, such as BFV, which is a scheme proposed by Brakerski and Van Verkouteren in 2012. And others use OT-based multiplication. So the difference as instance between the BFV and the Payet solution is that BFV is more suitable to pack together multiple plaintext, so we can perform computation in parallel, so batch multiple computation and do just one computation in the ciphertext. So it might be convenient to batch the operations and have a gain in efficiency, while OT-based multiplications are more efficient in terms of computation compared to BFV, but they require a bit more of communication. So depending on which application you're looking for, you might prefer one or the other. And concerning instead the top K selection, which is the second part of those linear scan, we have solutions that use the naive circuit computation. in order to find the top K elements, and some other use homomorphic encryption scheme like the BGP crypto system. So all the solutions seem to have a different approach, and the choices, of course, depend on what they are trying to achieve. But a common denominator that we find in all those solutions is that they use data sets which are quite small. To the best of our knowledge, the dataset that we saw used in this kind of setting have entries up to 10,000. At least the dataset that work on a two-party computation in a secure, in a honest but curious setting. There is a work in 2018 that has more entries, 50,000, but this work is done done in the malicious setting, and the query is processed in several hours. But anyway, no data set that we find past this 10 or 50,000 entries. And this is actually important when you look at the data set that we use nowadays that have entries that are way larger than a few thousand. And so the idea would be to find a solution that still solves this K neural network, nearest neighbor problem, but scaling up to very large data sets and still keeping a certain efficiency in to give you the answer to the request. So this is what our contributions try to solve. So as I said, the scheme we propose is called SANNS, and SANNS stands for Secure Approximate K Nearest Neighbor Search. So as I said, it's a two-party computation protocol where you have on one side the server, which owns the data set, and on the other side you have the client, which makes the query to the data set. And the goal of K nearest neighbor will be that the server at the end of the request learns nothing, while the client learns only the final result, so the K nearest neighbors element and nothing else, especially nothing about the data set itself. So as I said, the goal will be to keep the query, the result, and the database confidential all along the way. So in order to solve this problem, we propose two protocols that are based on approximate top K selection. So in order to have an improvement, we had to use approximate computations. And the first protocol that we present is an optimized linear scan, so very similar to previous solution, but with optimization. While the second one is new and is a cluster-based algorithm that achieves sublinear time. As I said, our goal was to find a solution that was scalable to large data sets, and we show with our experiments that we are able to treat the nearest neighbor problem. In particular, we do experiments for a 10 nearest neighbor search with data sets that contain up to 10 million entries. So in particular, we choose three data sets which are quite known, which are the dataset SIFT, the dataset Deep1B, and the Amazon Review Text dataset. And we show that we are able to achieve, as I said, the 10 nearest neighbor search with an accuracy of 0.9 in just a bunch of seconds. So when I say an accuracy of 0.9, what I mean is that in average, 1 out of 10 answer might be incorrect. And as I said before, we work in the security model, in the standard semi-honest model. And so we will compare with other solutions in the same security model. So this was a little bit an idea of what we're going to see today in this presentation. The rest of the presentation will be organized as follows. I start with some preliminaries. So I will describe the cryptographic tools that we use to build SANNS. And then I will describe SANNS in detail, so give you the two algorithms. And I will finish with some implementation results and some conclusive remarks and open problem. Of course, if something is unclear in my presentation, feel free to stop me and I will try to answer to the question or better explain the concept. Okay, so let's start with some preliminaries. So the ingredients that we use in order to build SANNS. So as I said, we're going to use multiple cryptographic primitives. And the first one is secret sharing. So for secret sharing, we use two flavors of secret sharing, the arithmetic secret sharing and the Boolean one. So in the arithmetic secret sharing, we share integers modulo t. This is a two-party computation protocol, so we will produce two shares, xa and xb, such that their addition is going to be equal to x modulo t. And then we have the Boolean sharing, on which we have a vector x, which is a binary vector of size tau. We will produce two share, again, xa and xb, which are as well binary vectors, such that their XOR is going to give us back the original x. So secret sharing in our protocol is going to be mainly used in order to connect all the other primitives inside the protocol. The second primitive that we use is additive homomorphic encryption in a private key setting. So additive homomorphic encryption is simply an encryption scheme that has an additive homomorphic property. So what does it mean? It means that when you have two ciphertext encrypted with an additive homomorphic encryption scheme, and you add them homomorphically, so you do an homomorphic computation on the ciphertext, the result is going to be a ciphertext encrypting the addition of the two original messages. So the operations that we can do with additive homomorphic encryption are not only addition between ciphertext, but additions and multiplications also between the ciphertext themselves and some constants. So in our scheme, so additive homomorphic encryption, as I said, was already used in the previous solution. We decided to use BFV as an additive homomorphic encryption scheme. So as I said at the beginning, BFV is a fully homomorphic encryption scheme originally, but we don't need the fully homomorphic functionality. We're going to use them just in its additive homomorphic setting. And in particular, we're going to use BFV, the BFV implementation that is provided in the Microsoft implementation seal. The type of packing we're going to use in BFV is a coefficient packing, so not the classical SIMD packing. And we're going to work on plaintext spaces modulo a power of 2. And we're going to try to achieve noise privacy by using some noise flooding, some circuit privacy, sorry, with noise flooding. Okay, so third ingredient in our recipe is going to be garbled circuits. Again, a very well-known technique proposed by Yao in 86. So GC allows two-party computation in order to compute arbitrary Boolean circuits, and is largely studied as well in the literature. And there are multiple improvements proposed to the original construction, such as the Frick-XOR, the ALF gates, and so on. So we implement again the GC in our construction, and we of course include all those improvements in the implementation. So in SANNS, additive homomorphic encryption is going to be used, as in previous work, mainly to compute the distance between the points and the query. And GC is going to be used mainly for the top case selection. So the fourth ingredient is going to be distributed DORAM. So why we need DORAM, sorry? Because we want to protect the accesses to the database. Again, there are multiple constructions in the literature. DORAM allows two parties to perform oblivious reads and writes on a certain secret shared array. And for DORAM, we decided to choose quite a new scheme proposed in 2017 by Dorner and Chillotti, which is called FLORAM. So FLORAM is a distributed DORAM scheme, very efficient, as all the DORAMs can perform read and write operation, but in our construction, we're going to just need it in the read-only mode. And when we implement it, we add some careful optimization in order to make it more efficient for our computations. So just to quickly describe the read mode of DORAM, the idea is that we have the two parties, and the two parties at the beginning are gonna hold identical copies of the data set. Of course, the database is gonna be masked. And the masking of the database is done with respect to a PRF instantiated with secret elements belonging to the two parties. So in the read mode is gonna get in input a Boolean share of the index of the particular place in the dataset that we are looking for. and it's going to give us in output a Boolean share of the database entry in the place I, which is masked. And at the end, we will need to unmask this database entry, and we're going to do it by computing the PRF to unmask the entry by using GC. And last but not least ingredient in our recipe is going to be k-means clustering. So as I said, we have two algorithms that we propose in SANNS. The first one is an optimized linear scan. The second one is a cluster-based algorithm. So in the cluster-based algorithm only, we're going to use the k-means clustering. So k-means clustering is an iterative process that allows to cluster the database. So if we call the database X, we're going to try to create clusters, which are disjoint subset of the dataset X. And for all of this cluster, we're going to find a center, which will reduce, minimize the distance with the points in the clusters. And so as I said, that this technique is going to be only used in our optimized algorithm. And as well as before, we're going to try to also adapt this technique to our setting and apply some little improvements to it. Okay, so those are the preliminaries. If there are any questions until now, I can take a little break and answer. Otherwise, I will continue. Nothing. Okay. Okay, so let's enter in the core of the presentation. So as I said, I will present SANNS, the two contributions of SANNS. So the first one is an optimized linear scan. Very similar to previous techniques for linear scan, what we're going to do is to compute the distance between the query queue and all the points in the dataset. So this computation, as before, is going to be done by using additive homomorphic encryption. In our case, the scheme BFD. And in the second part, where we have the top K selection, what we're going to do is to perform the top K selection with an approximate top K algorithm. So this top K selection is going to be done with garbled circuits. So the approximate top K selection is going to be used in both our algorithms, both the linear scan and also later in the clustering-based algorithm. And the idea is, of course, to, given a data set of endpoint, as before, try to find the smallest points in this data set in a sorted order. And eventually, we're going to also add a functionality which allows us not only to extract the values of those k smaller elements, but also their IDs. So the approximate top K selection that we propose tries to obtain an output which is approximately correct. So not all the output that we have might be correct. So there's going to be a certain accuracy in the answer. So it will work in the following way. In the first step, we take our data set as it is given, and we will apply a permutation on the elements of the data set. So this permutation is applied by the owner of the data set, and is going to be completely query independent. So once we have done this, this permutation, we start by partitioning the data set into L bins. Every bin is going to have the same size. And now inside every one of those bins, we're going to compute the minimum element between all the elements of the bin. And now once we have one minimum element per bin, we're going to just compute with the naive algorithm the k minimum elements between the minimums of every bin. So this will, of course, reduce, by accepting an eventual error in the answer, is going to reduce the circuit size from the naive approach that was of the order of B and K, where B is the size of the input, N is the size of the data set, and K are the numbers that we're looking for, the mean that we're looking for, down to B times N plus KL. And generally, or at least in our application, N is extremely large compared to K and to L. So this will result in an important factor of improvement. And in order to improve a little bit more this technique, we also use approximate distances. So instead of considering the entire b-bit input, we're going to discard the r lower bits. So r is as well a parameter that can be tuned in order to achieve a certain accuracy. And this will reduce even more the circuit size of the top K selection. Okay, so this was this algorithm, the top K selection, is actually the main reason why we have an improvement compared to the state of the art to previous linear scan algorithms. So the second algorithm is more new and consists in different steps. So it's our clustering-based algorithm. So this algorithm is able to achieve sublinear time to give us back an answer. And the reason why we go down to sublinear time is that we avoid computing the distance with all the points. So in the linear scan, as I said, in the first step, what you do is to compute the distance between your query and all the points. In this algorithm, we will not. So we will compute a certain amount of distance, but not all of them. So the approach is based on clustering the data set, as I said also, as I announced before. And generally, clustering-based approaches are not the best for k-nearest neighbor search in the clear test. But what we observe is that they are extremely suitable for secure computation. So we decided to use this approach, and we obtained interesting results. So the idea is that you start with your dataset, or at least the owner of the dataset, start by clustering the database by using the k-means clustering. And what we observe is that this clustering gives us very unbalanced clusters, so with different elements inside. So we modified a little bit the k-means clustering, and we introduced some sort of rebalancing in order to have all the clusters of the same size at the end. And eventually, if some are smaller, we're going to put some garbage inside. So the garbage generally is a point at infinity that will not disturb the Euclidean distance. And another improvement that we put in this case is to introduce a new structure that is called the stash. So the idea is that when we start clustering our data set, some of the groups that are produced are way smaller than the others. So instead of keeping them as they are, we decided to collapse them into a single structure that we call the stash. And this structure is going to be linearly scanned. And we observe that by linearly scan the stash is gonna be more efficient than just doing clusterings. So in practice, we're gonna have the entire data set is gonna look as you see in the slide, is gonna be composed by groups of clusters, balanced clusters, and the stash. So they're gonna be treated separately, and at the end, the result is gonna be merged. And of course, all the clusters are going to be associated with a center. This I forgot to say. Okay, so the cluster-based algorithm is going to work in the following way. I'm going to try to describe it by using this animation. So at the beginning, we start with initialize Floram. So we give to both parties, the owner of the dataset and the client, masked all the masked elements in the dataset. So they're gonna be injected in Floram in the initialization phase. So now that once we have the query, we're gonna start the query phase. And we're going to divide the query phase in two separate parts, one dedicated to the cluster and one to the stash. So, there's going to be also a permutation of the centers in the group. So the first thing that we do is to start by computing distances between the query and the centers of the cluster on one side, and the query and all the elements in the stash on the other side. So the result, this step is going to be done by using additive homomorphic encryption. Again, in our setting, we use the BFV construction. And after we compute all those distances, the result of the stash, so of the distances with all the elements of the stash, is going to be kept on a side. And we're going to continue on the right side of the protocol, so in the area dedicated to the clusters. So once we have all the distance with the centers, we're going to try to retrieve the approximate top centers, center IDs. So we have the distance between the query and all the center. We're going to try to retrieve the index of the centers that are the closest to the query. And this top K selection is going to be done in GC. Now, once we have the indexes of the top centers, we're going to try to retrieve the top clusters. So the clusters that correspond to the centers that are the closest to the query. And in order to retrieve those clusters, we're going to use FlowRAM in read mode. So we're going to read the clusters corresponding to those centers. And we're going to put all those closest clusters, let's call it this way, in a single big cluster that we're gonna treat in the following way. We're gonna start by computing the distance again between the query and all the points in this large extracted cluster. And then once that we have the distance computation for the clusters and the distance computation for the stash, we're gonna again do a top K selection on one side on the cluster points and on the other side on the stash points. And these two selections are going to give us back K elements on one side and K elements on the other. And we will end by doing a naive top K selection between those two K elements. And this is going to be the answer of the K nearest neighbor search. So again, to summarize, the query is going to be, we start by computing distance, select the closest centers, access the closest clusters, compute the distance between the query and the elements only in the closest clusters, and then do the naive top K computation in both sides and extract the final top K. So as I said at the beginning in the introduction, for AHE, we're going to use BFD, the BFD implementation that is provided by the SEAL library. For GC, we re-implemented GC in our implementation by applying all the existing improvements, or the major existing improvements. And for FlowRAM, we re-implemented FlowRAM, or at least the read mode of FlowRAM, and we try to do some little optimization. So in particular, for FlowRAM, we're going to change the PRF computation. So as I said at the beginning, the PRF is going to be computed to mask and unmask the elements of the dataset. And in FlowRAM, in the original paper, the authors use an AES-based PRF. So in our case, we decided to replace the AES PRF with Cribium. So Cribium is not a block cipher, as AES is a stream cipher that was presented in 2016 as a sort of an extension of the original Trivium stream cipher. So Cribium, the idea of Cribium was to be used in a fully homomorphic encryption setting to perform what is called transciphering. And so in order to be evaluated homomorphically on the cloud to decrypt, to re-encrypt the ciphertext, let's put it this way. So to be as efficient as possible in a fully homomorphic encryption setting, what the authors tried to do was to reduce the number of AND gates in the evaluation of Cribium. And this is actually very interesting in our case because we're going to try to reduce as much as possible the AND gates that we're going to evaluate in GC. And so Cribium becomes very interesting also in this context. And actually, we observed that Cribium in GC is more efficient than AES, about an order of magnitude better. So just at the beginning of the computations in the preprocessing mode, Cribium is going to be computed in plain text. And in order to be as efficient as possible, we massively vectorize this computation within AVX 512. Okay, so this is everything for the theoretical description of SANNS. So I'm gonna move to the implementation part. Of course, if there are any questions until now, feel free to stop me.
I had one question.
Yes.
So I was wondering, when you talked about this approximate top K selection before, you said that initially the data owner performs a random permutation of all the inputs, right?
Yeah, you compute the distance with the Q and all the inputs, yes.
Yeah, but so there's this algorithm where you had this list of numbers and you want approximately to get the smallest K elements, right?
Mm-hmm. Yes.
So in that algorithm, there was this initial permutation that you said was performed by the data owner, I think.
Yes.
So I was just wondering, in your actual application here, it would seem that the list of numbers of which you need to get the smallest ones would be secret shared among the parties. So is there a single guy who can do this permutation then?
It's only the database owner that does the permutation. And the permutation is query independent. Is it what your question was?
Yeah, well, I mean, how can I make this clearer? So I mean, the assumption must be that some party knows all these input numbers in clear, so he can locally.
Yes, the owner of the data set.
Right.
Yes.
But if the list of numbers where you want to find the smallest ones are not known by a single guy, but it's actually computed during your algorithm. I mean, you get the distance from your query to a whole bunch of other things, and then you want to get the smallest distances, right?
Yes. So yeah, let me go back just quickly to the. Oh, there is an animation, so it takes time. So here we are. So the idea is, again, stop me if there's something that I'm not understanding. So you have your data set, which is owned by the data set owner, and the guy is going to perform a permutation on those elements.
Yeah. Okay. So here's my question. So x1 to xn. I mean, obviously, if they are known to owned by a single guy, he can do the permutation. That's completely clear. It's just my impression that somewhere in your application, when you apply this algorithm, x1 to xn are actually distances from the query to a whole bunch of inputs in the data set.
Yes. No, right. They are just the elements of the data set. And then you're gonna compute the minimum of those elements in the data set. And then the only distance that you're gonna compute the mean between those means. So in practice, what you do is like you permute your data set, you compute a distance between the query and all the points, do a k-mean, a mean between those bins, and then extract the k-means between in all those bins. Everything is gonna be done like encrypted with additive homomorphic encryption, and the final result is going to be secret shared. So nothing is going to be revealed. So I feel like your scare is that something is going to be revealed.
No. I was just wondering how this was possible, but I think what you're saying is that this permutation that's being done here is actually the result of a big global permutation that's being done initially. And then it's
done initially by the dataset owner and is totally query independent.
Yeah. So okay.
So the actual dataset where you work on is the permuted dataset.
Yeah. Okay, that's fine. I think I know what you're saying. Good.
Okay.
Thanks.
Okay.
Hi, Ilaria. One other small question.
Yes.
How much do you pay? Let's say did you try, for example, for a clustering algorithm? How much do you pay by using your approximate k-min instead of like having a real k-min in terms of accuracy?
Yes, so we're going to show it in the experiments. We tuned in the parameters. Of course, you can choose the parameters in order to have better accuracy. So in our experiments, we were able to achieve 0.9 accuracy. So 90% of accuracy, which means that the answer that is going to be asked is to give us 10 k nearest neighbors point, and 9 of them in average are the nearest neighbors points.
Okay, great, thanks.
Thank you for the question. Okay, any other question until here? I'm gonna. Okay. Okay, so I show now some implementation results because of course we wanted to verify all those theoretic ideas in practice. As I said at the beginning, we wanted to test, of course, on large data set to show scalability. And we use 3 data sets. The first one is the SIFT data set, which is a standard database containing image descriptor that can be used to do similarity search between images. So the SIFT dataset contains 1 million entries, and every entry is of size 128. It's a vector of 128 elements, and each one of those elements is an 8-bit integer. The second dataset that we use is the Deep1B dataset. Again, contains image descriptors as SIFT, and those images come from feature vectors that are obtained passing the images through a deep neural network. So it's a very, very large database, contains 1 billion entries, each of them of size 96. And to do our computation, we decided to quantize the entries down to 8-bit size. So we don't do experiments on the 1 billion entries, but we extract 2 sub databases. The first one, we call it Deep1B1M, which contains the first 1 million images in Deep1B, while the second one, that we call Deep1B10M, is going to contain the first 10 million images of Deep1B. So the Deep1B1M dataset containing 10 million images is going to be the largest database that we use in our experiment. And the last database that we use is the Amazon database containing reviews for CDs and vinyls categories. So again, this is about 1 million entries, each of size 50. And we quantize the original entries down to 9-bit inputs. So for the queries, we use 10,000 queries for each database. In the case of SIFT, so the first one, the 10,000 query images are provided with the database in order to do experiments. In the 2 other cases, we just extract 10,000 images or words. We do experiments in the Azure platform by using 2 Azure instances that have up to 72 virtual cores. And we try to simulate in our experiments both a fast network and a slow network. So for the fast network, we decided to use 2 Azure instances, one in the West US coast and the other in 2 instances in the West US coast availability zone. While for the slow network, we use one in the West US and the other in the East US. So the latency, of course, will change. In the fast network, we have 0.5 millisecond of latency, while in the slow network, we have 34 microseconds. And the throughput is going to go from 500 megabytes per second to 7 gigabytes in the case of the fast network, depending on how many threads we are using in the experiments. And in the slow network, we're going to have a throughput between 40 megabytes per second to 2.2 gigabytes per second. Again, depending on how many threads we're using. And concerning the parameters, I don't report in the slides all the parameters. The details are given in the paper, but we optimize our parameters, as I was saying before, in order to perform a 10 nearest neighbor search. So look for the 10 closest elements to the query and to achieve 0.9 accuracy. So in average, 9 out of 10 of the answers that are given back by the algorithm are going to be correct. So a few numbers for the experiments. We use threads between 1 and 72. In the paper, we report results for many more threads, but in here, for a question of space, I just report for 1, 64, and 72 threads. So we do experiments, as I said, for the 4 database. And for all of them, we test the linear scan improvement and the clustering-based algorithm. So for the linear scan and the clustering, we do for both experiments in the fast network in the first line and for the slow network in the second line. So as you can see, the answer is going to be given back in a bunch of seconds. Well, for one thread, a bit more than a bunch of seconds. But as soon as we increase the number of threads that we can use, the timings decrease drastically. We are able to, at least for the clustering, to receive an answer in the fast network in less than 5 seconds, and around 20 seconds for the slow network. And something else that we can observe in this table, which is a bit strange initially, is that, of course, we have an improvement in the timing when we increase the number of threads, but this improvement is not linear in the number of threads. And actually, sometimes we observe that for 64 threads, we are even faster than for the 72 threads. About the same, but sometimes faster. And so this looks a little bit strange, and we need to investigate a bit more the reason why we have this behavior. But our intuition is that at some point there's going to be some memory bounds, bounds in accessing the memory, or bounds in the network that, of course, doesn't scale up in the same way as the number of threads, which will not give back better results. So even if we have more threads to do the computation, if there is a limit in the network or in the memory, this faster computation don't help that much. So that is why at some point we don't have an improvement. Okay, so those were the results for multiple threads. Now I'm going to give more details for at least for the single thread. In this slide, I also show you the memory that is used in the different stages. So we have 2 parts in the protocol, so a pre-processing phase and the query phase. So in the pre-processing phase, we have a pre-processing that is done just once per client, where the database are shared. And there is also an OT phase that is done once per query, that I didn't talk about before, but is necessary in one of the routines of Floram in order to generate some function secret sharing elements. So we're gonna just pre-compute the OTs by using libOT, and this is gonna be done once per query and before the actual computation. And so the query timing is exactly the same as you see in this table. And additionally, in this one, we have also the memory usage, which goes from a few hundred of megabytes up to a few gigabytes. But generally, in the cluster base, the communication is way smaller than the linear scan. So just to compare with the state of the art a little bit, so we compare at least the linear scan for the exact computation with our approximate computation and also the cluster-based solution. So we observed that in terms of responsive times compared to prior work in the same security model, the linear scan is able to achieve a speed up of 1.6 times for the fast networks and 3.51 in the slow networks. And the cluster is able to achieve a speed up of between 18 and 31 times compared to the previous solutions. Concerning the communication as well, we have an improvement. In the case of linear scan, the communication is 4.1 times better than before, and for the cluster base, about 39 times reduced. And something that, of course, is important to say is that in previous databases, which was one of the improvements in our protocol, is the database used were not that large, just a few thousands of inputs. And in our case, we go up to 10 million entries, so 2 orders of magnitude larger than previous works. Okay, so this almost concludes my talk. I will just finish with by summarizing what are our contributions. So as we saw today, we present SANNS, which is an algorithm for a construction for the k-nearest neighbor search. We propose 2 algorithms, 2 solutions. One is an optimized linear scan. The second solution is a cluster-based algorithm, which is sublinear. We propose, in order to improve these algorithms, a new approximate of case selection and also a technique to produce balanced clusterings. We show experimental results with databases up to 10 million entries, and our experiments prove that we are able to achieve 10 nearest neighbors with 0.9 accuracy in a time measurable in seconds. And as I said at the beginning, our solution is in the semi-honest security model. So this last point of the summary brings me to the first point in the open problem. So the first open problem is, of course, to try to extend our construction for other security models, such as the covent model or the malicious model, the malicious setting. So as I said at the beginning, there was a construction doing k-nearest neighbor in the malicious setting, analyzing the data sets up to 50,000 entries, and the response was given in a few hours. So it will be nice to see how SANNS behaves in a malicious setting. Of course, we expect an important slowdown, but it will be nice to see how much is this slowdown. The second open problem would be to try to use other techniques that are used in the literature for k-nearest neighbor search in SANNS. So we use a cluster-based algorithm, but it will be nice to see, as instance, how local sensitive hashing will behave, which are largely used in the plain text setting or other primitives. And last open problem, something that we would like to study, and we didn't have time for this paper, is to study more in detail the leakage of our algorithm. So we would like to see if giving queries back will reveal more than simply the result or something more about the database. So we are aware that there are works that study this information leakage for small databases, but we are not aware, or at least to the best of our knowledge, there are no works that study this problem for large databases. So we would like to study this problem, and especially we would like to understand if giving back an approximate answer to the k-nearest neighbor search will leak more information than what we expect. So this, of course, is left an open problem, and is going to be studied on a future work, we hope. And so this is all I wanted to say. Thank you for your attention. I think I'm right in time. And of course, if you have any additional questions, I will be happy to answer. The following slides are just sources for completeness. So thank you very much.
Thank you very much for the talk, Ilaria. So if anyone has any questions, then feel free to unmute yourself. Otherwise, for now, there is one question in the chat from Alexander.
Do you want me to read it?
Yeah, go ahead, if you can see.
I have to look for the chat. Yes,
I found
it.
Okay.
Is the Q&A? Yes. So do you find any data sets where SANNS was less accurate? We just did experiments with those 3 data sets. I would say that the accuracy depends on how you set your parameters. So how you choose the size of your clusters, how many nearest neighbors you're searching, how many beans. So it really depends on many, on the parameter settings. So I suppose that not even changing the data set, just changing the parameters, you might have a different accuracy, but of course, you will have a different execution time or memory consumed in the communication. So those are the only 3 data sets that we tested. So yeah.
Maybe a follow-up question to that. Did you find that the way you had to tune the parameters to get good accuracy, was that a very different way to tune them, depending on which data set you were looking at?
I can give you this answer by giving you the actual parameters. I will check the parameter choice because I don't have them in mind. Do you see the paper that I'm looking at? Or you still see the slides?
No, we don't see the slides.
You only see the slides. Okay, I'm checking the parameters. So of course the choice of the parameters is different, but the, how can I say, the order of the magnitude of the parameters, the order of magnitude of the parameters is correct in English to say it, is about the same. So if in one data set we have about 100, we're going to be also in the other data set on the 100 size and so on. Okay. So they are about, they are very similar in terms of size for all the databases. I cannot tell you if you change them completely, how it's going to be the result. Of course, accuracy will change, timings will change, but I don't have an intuition to say how. Yes, I don't know if it answered the question.
Yes, thanks.
Okay.